Hi, my name is Tomasz Tuzel. I'm with Ristretto Information Security. I'm here to talk to you about a project we did named Ristretto. Ristretto is basically a look into the possibility of using hardware enforcement to create a sub-Turing complete environment for a program. So basically, we're just trying to make a more safe and secure development environment for programmers and make analysis more straightforward. So Ristretto's goal was to protect vulnerable software with compilation and runtime protection. So we wanted to dynamically be able to detect code that was of interest to us, create an execution environment that was sub-Turing complete, and make those transformations automatically. We did the hardware enforcement with a feature that Intel provided us called Intel process tracing. I'll talk about it a little bit more in future slides. So a little bit of background information. Weird machines. Weird machines are basically a situation where a program is executing outside of its normal spec. So if you think about a situation where you have a ROP chain exploitation or something like that, that would be putting into weird machine state. The two things we leverage for this project are LLVM and Intel PT. LLVM is basically a tool chain that has a lot of things in it, but we're specifically interested in the IR, intermediate representation, GIT engine support, and the Clang compiler. So Intel processor tracing was something that was introduced by Intel back in about 2015 for the Skylake processors. I understand there's some cases where it was available before that, but and it has about a 5% overhead from our work when we did our testing, and also from other people's work. They came up with about 5% as overhead just for the tracing part. So what's the problem we're trying to solve? Basically, Turing complete languages are very powerful. They give a lot more. They deliver a lot more power than a developer may necessarily need. And so that sort of opens up the door for a lot of weird machine behavior. We did some work about a year ago, I believe, for a project named Mocha that looked into the possibility of making the Linux kernel sub-Turing complete wherever applicable, and we found out that about 90% of the kernel was a candidate to be made sub-Turing complete. That's a pretty decent metric for whether or not you could extend that kind of sub-Turing completeness to other simple applications or not so simple applications, because the Linux kernel is, for one, quite large. It also has a lot of other components to it, like event handlers, which certainly don't terminate. So you can kind of extend that to understand that if 90% of Linux kernel can be made sub-Turing complete, then many other applications can probably be done similarly or better. So we are sort of in this circle of bugs where you have a complex data format, you have a complex parser, you have analysis you're trying to do, which leads to bugs, and then we try to reactively deal with them by writing signatures, which is certainly not the best way that things are going, but that's how they are. And at the center of that is input parsing, which you basically have a program which an attacker has control over to put in whatever type of input they want. If they do it right, they can drive execution flow and put the system into an untrustworthy state, which is hard to model, hard to deal with, and hard to understand, hard to predict what they're going to be doing in a Turing complete environment. So we can't really produce proofs of what that's going to look like, because you have a situation where there's basically a state explosion. There's so many states that we can't possibly fully understand them and fully model them all. So you sort of end up in the situation where as the language gets more powerful, the more difficult it is to analyze. Automated analysis tools don't really work. It becomes impossible to understand whether or not the program is going to halt or not. So you have this kind of an undecidability cliff. So, okay, so that's all bad. What did we do to try to work towards a solution? So we took LLVM passes, which a pass is basically a way to change an intermediate representation to a different type of intermediate representation. So LLVM supports passes for a couple of different things, loops, functions, that sort of thing. There's a whole bunch of other ones. We are in particular interested in the loop pass, and we can mark them for unrolling and forward-only enforcement. So we do exactly that. We enroll them to a forward-only situation to try in areas of interest, and we can enforce the forward-only behavior via Intel PT. So a little bit more detail on what we specifically did. Well, you take a program, compile it to the IR, and then you run an analysis to identify whatever loops are of interest, unroll simple ones. So a simple loop means if you take, for example, a C for loop, for I equals 0, I less than 10, I plus plus, that's a simple loop. We know it's going to terminate at compile time. We just unroll that one right away. For a more complex loop, think about something like I equals 0, I less than j, I plus plus, but we don't know a j is at compile time. That's a more complex loop. So we leave that one to be a JIT, handle that JIT by putting it into another function and dealing with it at that point. For the hardware enforcement, we can insert start and stop traces. That can be done automatically or manually. There can be times when a programmer just wants to make sure that they are securing certain sections of the code, so they can put that in manually to enforce that, like at the start of a function in libc or something like that. And so with Intel PT, we can trace data and do parsing. So we can detect if a branch has gone to a lower address, which may not be what we want if it's inside the start and stop trace. And then as of right now, we currently are parsing the target block after it's executed, but there's not really any reason we couldn't do concurrent parsing. It's just a question of man hours. Okay, so that's what we set it to do, and that's what we are able to do successfully. So in the actual implementation, we can unroll simple loops and handle complex loops JIT. Forward-only enforcement does work in every case that we were able to test, and we also were able to handle some unexpected instructions. So for example, if we can model something where if it returns to an address that we don't expect it to return to, we can trap. That's something that can be extended. It's just something we sort of played with for a little while. So we did all that. Is this actually effective at stopping exploitation? So in order to answer that question, we did a little bit of testing by creating, by looking to see if we can create a forward-only wrap chain versus just, and how successful we were with that versus just doing the simple wrap chain without any of this enforcement. So this is an extremely stupid, simple way to visualize it. I have an actual partial wrap chain on the next slide, but just to sort of illustrate what we're doing. For anyone who's not familiar with what a wrap chain is, basically, if you have a non-executable stack, you can't just look for, say, a buffer overflow, copy your shellcode in the stack, and execute the shellcode. So what you need to do is find code somewhere you can execute it. So you can put some data on the stack that you need to return to the proper addresses, find some gadgets throughout your executable environment, and jump from them. So you basically create, so you need to find wrap gadgets throughout your code. So in a normal environment, you can jump all over the place in your code from any addresses you want, from lower to higher, higher to lower. So in the above example, you're going from one to the next, and then skipping one and going to the last one, going back. Whereas in Ristretto, you can only go forward. Whereas you can skip certain gadgets. You can, if you try to go back, you'll get told off by Intel PT. So here's a bit more of an illustrative example with a partial wrap chain. I just pulled out enough to be able to show you without it being so small you can't read it. But basically, the arrows kind of help show you that, on the top one you have lower addresses to higher addresses, lower addresses. In some cases, it actually repeats the same gadget. In Ristretto, it can only go forward, which is at the bottom. So in order to do this and answer this question, initially we tried to just do one by hand, which was about as miserable as you'd expect. There was no situation that I found that I could actually do this. So we took a tool named Wrapper, which is freely available on GitHub, and modified it to be able to support and only do forward-only, find a forward-only gadget, forward-only wrap chain. So, and basically what it would do is, you tell it to go, and it would start from the first gadget it could find, work its way down, trying to find something that fails, it would go back up and try again for the next one down, all the way down. So it was a lot, and so we tested this across a bunch of different gadgets, a bunch of different binaries, including for Linux, we tried to do execve, some sort of execve to execute binsh, which is a pretty traditional way to do a wrap chain, or run mprotect in virtual protect for Windows. And so in Linux case, we just made a really simple libc statically linked elf binary, which I think it just had like a printf and just statically linked in libc. And then MySQL daemon, because it was big, and we did that for x86 and x86-64. And for Windows, we just used Windows CMD and a cygwin bash.exe for x86 and x86-64. In all cases, this thing failed across the board. There's no case where it could find a wrap chain in a Ristretto case. Even in cases where we had a wrap chain failure in a normal environment, Ristretto would still cause it to fail very early on. So we'd sometimes not even be able to get past the first gadget in the chain. So it did a pretty good job overall. So the performance impact of doing this with Intel PT, I mentioned before, about 5%. That's what we found in our testing. That's just for the tracing part. For the parsing, the overhead comes out to about 200%. This is still very initial research, so that could be whittled down quite a bit, which I can talk about a little more in a bit. And for the JIT enrolling, that was also a pretty substantial hit, but that's not very common to encounter a situation where you need to actually handle a loop JIT. And as a result of that, we actually had a difficult time testing it because there's not many samples of that to base our overall performance hit off of. So what can we take away from this? Well, this path forward sort of gives a ability to be able to handle software and formally verify some software that we previously couldn't because it was Turing complete. It can automatically limit some risks to certain types of programming practices and sort of hand those tools over to some programmers. So there's a lot of future work that can be done in this respect for a lot of this work. So I mentioned concurrent parsing before. That's certainly something we can do. It's just a question of manpower. There are other enforcement mechanisms that are out there that could be leveraged to substantially increase the performance of this. I believe that ARM actually supports certain types of branch sharpening in the hardware. There's also the ability in ARM in the hardware level to do forward-only enforcement, so that would be certainly something to look into. It would, in that case, actually eliminate the parsing cost entirely. And we could do some more performance testing with JIT, which I mentioned before. We had pretty limited sample sets to actually get a full semblance of how substantial of a performance impact it has on us. There's various other testing we can do, test more binaries, that sort of thing. And since we, given all this work, there's a lot of other techniques, like I mentioned before, that we can do with if we don't have to worry about termination. And also, since we can recognize certain areas of the code automatically that are subject to possibly being in danger of, causing weird machine state, that kind of lends itself to mean that even in a compiler environment, we can recognize certain areas of the code that could be made more simple, more secure, that sort of thing, and warning a developer on the fly that maybe they should consider rewriting something in a different way. On a different note, there's also the possibility to look into something like a subset processor. So think about this in a sense of, you don't need to actually have a physical separate processor, but it's maybe easier to visualize in that respect. So like a GPU has a FPU that only does floating point operations. So if you had a separate processor that can only do forward-only execution, or can only do certain types of memory access or something like that, we could isolate that kind of execution to that hardware and isolate it that way separately. We could also look into making our passes a bit more general so they can make it easier to port, and even retroactively go back and look at some existing binaries by using a binary lifting tool like MCSEMA, which is a tool provided by Trail of Bits, which lifts a binary into LLVM bitcode, and doing our operations on that moving forward. There's also certain things like looking into doing dynamic microencoding to do this kind of thing on the fly. Anyway, I'd like to thank DARPA I2O for sponsoring this work, as well as Sergey and Helver for their input and support. Any questions?
So you mentioned Intel PT. I'm curious if there are other such hardware mechanisms for other CPU architectures.
Not that I'm aware of, except for the ARM one. Admittedly, I haven't looked into it really that much.
Okay.
But ARM, so I'm told, and I'm trusting one of our other developers to tell me the truth on this one. He told me that that ARM actually allows you to trap on certain unexpected branches and actually enforcing the hardware forward-only branching, or sorry, forward-only execution.
Oh, wow.
So as far as the other ones, I'm not really sure about the other architectures.
Cool.
But I mean, now that you asked that question, I would think so. That would make sense to me.
Thanks.
I noticed, I was interesting that you were exploring the effects of this restrict execution model and arbitrary programming. Have you looked at any of the other more advanced forms of code reuse attacks? A lot of those have been developed to try to execute in more restricted environments where was defeated by these control flow techniques. Fairly large body of work in that area. I was curious if you explored any of that.
No, we haven't. Not really. It's probably something we should put on our plate for future work.
I don't believe any of them are specifically focused on only going forward, so to speak.
Mm-hmm.
So I don't know that it may well block all of them, but I guess the interesting thing would be whether it's possible to create a more advanced form of a reuse attack